So today we are going to expand the concepts which we have learned from the first two sessions, and we'll deep into the world of Central Limit Theorem. We'll go much deeper into the world of Central Limit Theorem, which I believe is one of the most powerful inventions in the world of statistics, because a lot of problem can be solved using Central Limit Theorem. Apart from that, we'll also understand how we can use actually z-score and p-value. So in the previous video, we have seen how to calculate z-score, and here we'll see how to use z-score and p-value. And in the process, we'll also understand the difference between population and sample. So population and sample. And this will pave the way for us to dig deeper into hypothesis testing. So let's get started with understanding the use of z-score and how is it related to p-value, and what is p-value and how is it so important. So let's get started. So in statistics, we do two major varieties. One is descriptive statistics and one is predictive statistics. That means we want to predict something, right? Suppose if I give you a problem, right, or I give you a scenario and I ask you what will happen next, which means essentially means that you have to predict something. Like for example, if I tell you say who will be the next president of, say, USA. As you know, the presidential elections are coming. So if I ask you who will be the next president of USA, and I hire you as a statistician and I ask you to make some predictions. Suppose we have candidate A, suppose the two main candidates are candidate A and candidate B. Now, if I ask you, tell me what are the chances of candidate B being the next president of USA. Now, what you can do is you can collect a lot of data. So you will collect a lot of data in the form of maybe opinions from different people, different agencies. You will collect all the data, do some analysis, and if you have to find out who will be the president of USA and what are the chances of candidate B being the president of USA, you will analyze this data, for example, and then you will come up with something called a p-value. So if I ask you, tell me what are the chances of candidate B being the president of USA. So you collect a lot of data, then you calculate something called p-value, and this p-value, in this case, if we just want to find out the chances of candidate B being the president of US, So we basically say, we ask different people and say, will you vote for candidate B? Will you vote for candidate B? Right? And you get yes, no's and everything. Now, after doing all calculations, how to do all the calculations and everything, that let's just park it. We'll look at it. Suppose after doing all the calculations, we find something called a p-value. Okay. Now this p-value basically denotes the chances of candidate B being the president of US, because the entire analysis I am running on this particular hypothesis, that what are the chances of candidate B being the president. So we analyze the data, we calculate something called a p-value, and suppose if we get a say a p-value of 0.8, for example. Now that means that the chances of candidate B being the president of USA is 80%. So we take the data, we take a hypothesis to start with, we collect the data, we do the analysis, we calculate the p-value for a particular incident or a particular question. So first is we build some kind of question or hypothesis. We'll look at in a bit more detail with hypothesis testing. So if you are already aware about hypothesis testing, some of these things may look as if a bit disjointed from that hypothesis testing. These hypotheses right now, don't worry about hypothesis testing. Just think of it like a belief at this point. So you should think like this, that we have a hypothesis, we collect data, we do some analysis, and then we get p-value. Now after doing all these things, so this is my hypothesis, right? This is my hypothesis with which I am working, and after doing all this, I get a p-value of 0.8, which means that the chances of candidate B being the next president of USA is 0.8. However, having said that, when we talk about null hypothesis and alternate hypothesis, we'll see a slight difference from what we had just said. I mean, we do it a bit differently, but the basic principle is this. I have hypothesis, I take the data, I do some analysis, I calculate the p-value. And here the hypothesis, as I said, is candidate B being the president of USA. Okay, so I am asked these questions: what are the chances of candidate B being the next president of USA? And my answer is, going by all the statistical analysis, the chances looks like 80%. Okay, so p-value gives me the chances of a particular incident being true. Here the incident is that candidate B will become the next president of USA. I guess it's clear so far. Now what we'll look at is how p-value is related to the z-score. Z-score is something which we have seen in the last lecture. If you have not watched the last lecture, please go and look at the last lecture and then come back to this lecture. So now let's look at how z-score and p-value are connected. So let's take a normal distribution. So this is a normal distribution, not a very well drawn normal distribution, but I think to some extent at least we are able to understand it's a normal distribution. Fair enough. So suppose this is my mean. And say my mean is 50 and my standard deviation is say 5. So simple one only. This one is 55. This is 60. This is 65. This is 45. This is 40. This is 35. So as you can see, I since the standard deviation is 5, I have gone up to 3 standard deviation to the right and 3 standard deviation to the left. Now, suppose I ask you a question that what are the chances? Suppose this is a distribution, right? So behind the distribution, what is there? How do we get this distribution? So we have data. From this data, we can draw this distribution, and this side maybe this side is my actual data elements, and this side is my frequency. So from the actual data, which has got rows and columns, and the actual data can probably range from say 0 to 70, 20 to 70, for example. Suppose this is my data. From these data, I have drawn this graph, which looks like a normal distribution. Now I ask you that suppose from these data, I pick up a random data point. Okay, these data, suppose here I have data, which is nothing but rows and columns, right? Any data is nothing but rows and columns. In this case, this is only one. It is only one column which we are looking at. Actually, I should not call it as a rows and columns. In this case, this is just one column. Multiple rows, right? So now, if I ask you that what are the chances if I randomly pick up one row from this particular data, which looks like this, what are the chances that will be less than 65? Will it be very high? Will it be low, or what? So if I ask you that, hey, you know what? I have this data and I know that this follows a normal distribution. What are my chances that I will pick up a data point which is less than 65? When I say I pick up a data point, I can randomly choose a data point. I do not know what the data point is. I just want to understand what are the chances of it being less than 65. Similarly, say what are the chances of a random data point being say greater than 45? What are the chances of a data point being less than 30, say 32, for example? So let's look at these examples. Okay, so in this case, what are the chances of me picking up a random point which falls anywhere in this distribution? Think intuitively. Right now, nothing. Don't worry about anything. Intuitively, do you think the chances should be more or less? On a count of 3, 2, 1. The answer is the chances should be very high because the entire distribution is on this side, right? So if the chances are high, it is very good. How high? How much? Just quantify. Let's quantify with a number. So what we'll do is we'll calculate first the z-score of 65. What is the z-score of 65? That is x minus mu by sigma. So in this case, x is 65 minus mu, that is 50, divided by 5, which is 15 by 5 is 3. And we also know that it's 3. So this is 3. The z-score is 3, which is okay. But how do I convert that into a probability, into a p-value? So for that, we use something called a z-table. This z-table you can just Google and you will find, you can download this z-table. It's not something which I have built. It's already there in the internet. You can download it and you can use it. So if I come to z-table, the way to read z-table is, so here we got a z-score of 3. So from z-table, what we get is p-value. So in z-table, what we can do is, we can pass the z-score and get the p-value. So let's look at the z-table. So here the z-score is 3. So 3.0 and here is 0, 0. So that is fine. So 3.00 will be this point. That is 99.87, which is okay, 0.9987 or 99.87%, whatever. So let's come here. So what it is saying is, if this point is my point in question, which means if this point is 3, which in this case it's 3, here this is like 50 and this one is 65, the z-score is 3, which means the chances of anything picking up randomly from the left hand side of this point in question is 99.87. or a p-value of 0.9987. Now if I ask you what are the chances of picking a random data point from this distribution which is greater than 65, that will be 1 minus, which is this side. If the total is 1, then this will be 1 minus 0.9987, which is 0.0013. Not 13%, 13, and then you can multiply it with 100 and you will get 0.13%, right? So let's drop this off. So let's look at few more examples. So the first answer what we got is Now less than greater than 45. Greater than 45 means I want this side, right? The right hand side. And intuitively we can see that right hand side should be more. Greater than 45, the chances of you picking a random sample which is greater than 45 is actually more. Now how much more? That's the question. So 45 we can clearly see that z score of 45 will be -1. How? Because here it will be this will be, if this is 45, if this is 45, then this will be -1. So here the z score is -1. Now what that means? Now let's go to the same z table. When the z score is negative value, then we come here. So here we got a z score of -1, which is this point. However, here, which means the shaded region percentage is what I have got. So the number which I have got is 0.1587, right? How did I get there? Again, let's come back. A z score of 1, and here this is 0, 0, which means the value which you are getting is actually this side of the curve, and I want this side, which means if this side is 0.1587, then this side should be 1384, which means 84.13%. So the chances of we picking up a random point is greater than this point in question is 84.13. So for a negative z score, we get this side, which is this value, but we want this side greater than 1, greater than 45, z score greater than 1, this region. In this case, this z score, this is 45, so I want this region, and the chances is 84.13%. So let's come back. This is next one, less than 32. Less than 32 is should be this side and should be very, very low. Just intuitively, if this is 32, so for me picking a random point here should be very low. Intuitively we know that. So just let's look at 32. So if we pick up put 32 here, we get -18 by 5, which should be -3.6, I guess. -3.6. So let's see if you can find -3. Oh, -3.6 is not even here. So let's pick up say 34. Say let's do 34. So this 34 should be minus 3.2, which means the z-score is minus 3.2. So less than 34 means this region is what I'm looking at. And intuitively, we can see that it should be very low. Let's see how much. So 3.2 is this much, is this value. So 3.200. Had it been like say 3.21, then we would have picked up this value. Say, let's say, can we pick up minus 2.77? So minus 2.7 is here, and 77 should be this point. 2.7 and 77, and that should be this point. 2.7 minus and 7. Similarly, say minus 2.14, minus 2.14. That's how you should read the z table. Okay. So now minus 3.4, 3.2 is what we have got, which is 0.007, which means this side is 0.007, which means the chances is 0.07 percentage, very low. So 0.007 is the p-value which we have got. Now we have to multiply it by 100 and we get this. So greater than 70, let's do the last one. Or maybe say, yeah, let's do greater than 70 is actually a high number is what I feel. So let's do say greater than say 57. Greater than 57 means this point. This should be 57. And greater than 57 should be this region, which technically through naked eyes looks very small. But how much small? Let's figure out. So this is now 57. So this is like 7 by 5. 7 by 5 is 1.4. So now let's come to the Z table. Let's take 1.4. So 1.4 is this much, which means region to the left is, so what I want is this point, right? This is my z-score of 1.4. I want this region. However, the value which we'll get here is actually this region. So this is this region. Right? So this one is 1 minus 9192, which ideally should be 0.08, which means if I just multiply it, it should be around 8%, a bit more than 8%. Okay, I hope this part is clear now, because this is the foundation, this is the base which will help us to solve a lot of problems. So we have completed Now understanding z-score and p-value. Now we'll understand what is a population and what is a sample before we go to central limit theorem. So population and sample. So in very simple terms, population is my superset and the sample is my subset. So population is a superset and sample is a subset. Now let's get some examples. Suppose I ask you what is the population of India, which means it like contains the entire population of the country, which should be around approximate say 130 billion, 130 crores, right? 130 crores population of India. Now suppose if you have to do an exit poll, right? If you want to do an exit poll, do you think it's feasible that we go and ask all these 130 crore people that whom did you vote for? It's impossible, right? So what we do is we create subsets. We create subsets where we divide people by age, gender, occupation, mother tongue, and so on. Lot of criteria, not only these four. And then we pick up few people from here. We pick up few people from here, we pick up few people from here, we pick up few people from here and ask them. So suppose here we have got say multiple age groups. So suppose for age group 60 and 70, we have say 5 crore people. So we'll not ask all those 5 crore people. We'll go and ask say 2000 people who will represent this 5 crore people. That's something which we assume. Now, while sampling, a lot of errors can come if the sampling is not done correctly, right? So by age, gender, occupation, mother tongue, and so many other criterias, that's the statisticians uses and then chooses a subset from the superset and does the statistical analysis on the subset, because it's impossible to go and ask 130 crore people whom did they vote for, right? So maybe out of these 130 crore people, they will ask say 1 lakh people, and with good statistical agencies, they can, if they do the sampling correctly, if they choose the right set of subsets, then 1 lakh, 1 lakh 50,000 or even less. I mean, the more expertise you have, the less subset is what you require. And then based on that, based on these 1 lakh, we make decision for these 130 crores. That's the power of good statisticians. In some agencies, it's even less. I have seen agencies who have done exit polls for just by selecting 50,000 people out of a population of 130 crore people, and their prediction was like very, very close, right? So it's not possible that we go and talk to everyone. So we choose a sample, we choose a subset from the entire data set, and then we do the analysis on that, and we assume that this subset represents the superset. Like for example, suppose all these are my data points. All of them are like one individual. And dot dot dot. Now we can choose subsets like this. And it's important that the same subset can be repeated, which means the person who represents a certain age can also represent a certain gender. There is no hard and fast rule that for each experiments or while choosing each subsets, we only choose the unique set of people. Not necessary, right? So we can choose like this. Here we are just choosing four, one set with four people. So for each sampling criteria, we are saying say pick four people. Though in exit polls they do not pick four people, so don't mix it up with that. This is just for representation and for this purpose, just for understanding purpose. Suppose for example we pick up four people each, and we choose from here. Say here also I say choose four people, and then we do the analysis independently on these guys. We do some calculations, and then whatever result we find, there is something which we can tie back to the main population, and we can say that the results which we have got from these samples or this subset is a representation of the entire population. So now I think we have got a fair idea on population and sample. Now keeping this in mind, we are going to understand central limit theorem. So let's look at central limit theorem through an example. Say I have a data set where I have around 20 records. So here, as you can see, I have got 20 records. Around 20 records. Now what I'm going to do is, I'm going to randomly choose, by the way, here, the word which is very important is random. I cannot pick and choose at my wish. I cannot say, okay, I want this, I want this, I want this, I want this. No, that will not work. I have to randomly just close my eyes and pick up four people. Similarly, in the previous example, when I was showing is when they create subsets. Suppose they have created a subset where all the occupation is say IT professional, right? Now they know that these 20 crore people are IT professionals, and I know that okay, I want to choose say 50 people from there. I cannot make bias in my mind and say, okay, I want these people, this. I'll suppose think like this, as if I'm closing my eyes and I say, okay, number 21,000, okay, number 15, okay, number 30. So it's like randomly I'm choosing. Because if I do not choose with random or randomness, then the entire purpose gets defeated. The tests cannot be done on bias. It has to be random. So suppose I have randomly picked up, this is something which I have already done before, so that I don't lose time in doing that. So just assume that okay, I have not done any cheating and I have randomly picked up. So suppose I have picked up these four numbers randomly from here, 5, 7, say 32, and say 11. Last one. And once I have picked up these 4 people, what I have done is I have calculated the mean and the standard deviation. So this is like a mini distribution. This is the main distribution. Main distribution, I call it as a population. And say this is a mini distribution. So I pick up these 4 numbers. After picking up these 4 numbers, I take the mean and I take the standard deviation of just these 4 numbers. Again, I pick up again 4 numbers from here, which are these ones. Again 4 number picked up from here. I calculate the mean. I calculate the standard deviation of these 4 numbers. Again 4 numbers here, the mean and the standard deviation. 4 numbers, the mean and the standard deviation. Okay. Now what we shall do is, let's come here. Standard deviation is something which we do not need. We'll work with the means. So for all these subsets which we have taken, for all these 4 number subsets, we have got the means for all of them. We have also calculated the standard deviation, but we do not need it. So we have taken all these means. So as you can see, these means. So we have formed another data distribution where we have taken all the means. So these ones and these ones, all these means. And we have formed another data distribution because the collection of data is a distribution. So here we have created a distribution of means. So we have taken all the means and created another separate distribution. Now, what central limit theorem says is that when we have formed this distribution of means, if I plot them, then if I plot them, plot a frequency, what I get is a normal distribution. Of course, I have to do some some amount of sampling, which means if I just take 2 samples, if I just take this one and this one, I'll of course not get a normal distribution. So we have to do substantial amount of sampling, and it depends on how much data you have. The more data you have, the more number of sampling you need to do. So central limit theorem has got 3 distinct and very important formulas. First formula is, when you form a distribution of means, if you plot them, if you plot their frequency, you will find that they are following a normal distribution, which is, that means this particular distribution, if you plot, we find that it follows a normal distribution. That's the first hypothesis. Second hypothesis is, since this is also a distribution, I can take its mean also. I can take the mean of all these numbers, and suppose I have done that, and I can see that this is 44. So this mean is 44 is what we have found. Ignore all this right now. I'll talk about it in a moment. So all these numbers all these particular numbers. Like for the distribution of means, if I calculate the mean, which means mean of the distribution of means, if I calculate, I get it as 4.86. Now if I call this as a mu bar, this mu bar is 4.86. Central limit theorem says that these mu bar and the mu, which is the mean of the population, mean of population, right? After some time, these two will come very close and can be equal also, or even if it does not come, even if it does not equate, it will like come very close. So these mu bar will come very close to mu. So here this is 4.86. Let's look at what is the original mean. It's 45, and we can see that after 20 iterations of randomly picking up numbers, what we find is that the mean of this distribution of means, they have come very close to the original population. That's the second hypothesis. So we have learned two things from central limit theorem. One is distribution of means when plotted will form a normal distribution. Will form a normal distribution. This mu bar is mean of distribution of means. And this is population mean. Point number 3, third hypothesis is sigma x bar is equal to sigma by square root of n. Sigma x bar is standard deviation of distribution of means. This is standard deviation of the population, and this n is number of samples. So in this case, if I have to run the central limit theorem, I have to ensure that this n is constant, which means every time I have to pick only 4 or only 5. For one iteration, if I just pick 4, second one I pick 5, then I will not be able to apply central limit theorem. So here also, if we see, if we calculate the standard deviation, this is 14.34. What is the standard deviation of the population? 25.5. If I divide it by square root of 4, which is 2, it should come to 12.77. And we can see that here we are 14.34, and it's coming very, very close. So you must be wondering what is these numbers. So when I had taken the first two data point, first two means, this was my mean of the distribution of means. Then first three, this, then first four, this. And as you can see, with time and time, the more iterations we do, this is coming closer to the original distribution. Here also we can see that this is decreasing and coming close towards this 12.77. Ideally this should be 12.77, right? Because if you look at the formula, sigma is 25 and we have taken 4 samples, so 25 by square root of 4 is 2, that comes to 12.77. so this side is 12.77, and after a few iterations this is like 14.3, and it's coming closer. If you take few more iterations, it will eventually go and come very close to 12.77. So in essence, these are the three formulas of central limit theorem. Now couple of things which we have to understand, which are the assumptions. So number one, the population can be of any sample, or sorry, the population can be of any kind of distribution. Does not mean that the population has to also be a normal distribution, not necessary. So the first assumption is population can be any distribution, can be skewed, can be normal, can be anything. Can be any kind of distribution. Number two, when we choose the sample, we have to choose them randomly. So random selection. That's important. Number three, samples should be independent, which means if I pick one sample, the selection of other samples should not have any impact. So let me independent, which means, for example, if I choose 5, this 15 has no impact. So I have chosen 5, then I've chosen 15. A 15 has no impact whether the previous number we chose was 5 or not. It's independent. It got independently chosen. So we have closed our eyes and said, okay, 5, 15, 12, 14. So 15 has no relationship whether we chose 5 before it or 32 after it. So that's another assumption. So the next assumption is the sample size which we should choose, that should not be more than 10% of the population. Should not be greater than 10% of the population. And number 5, if the population is like asymmetric in nature, like right skewed or left skewed, this is not left skewed by the way, if they are asymmetric, which means say this one or this one, then we need to choose more samples. And if they are symmetric, then we need to choose less samples. So for symmetric population, or in simple terms, things if the distribution is like more or less normal, then we can limit the sample size to less than 30. We should choose sample size which is less than 30. For asymmetric population, we should choose more samples. Okay, I hope these assumptions are clear. Now what we'll do is we'll run through a quick simulator where this concept will be even more clear. So this is the link of the simulator. You can also go and practice yourself. And when I learned central limit theorem for the first time, I got very confused initially. And then I used this simulator and everything started to make sense very quickly. So let's look at the parent population. Say parent population. We say that it doesn't matter what is the parent population. It can be normally distributed, non-normally distributed, can be anything. Now what I'm going to do is, so I just distorted the population as much as possible. So for this population, I know the mean and I know the standard deviation. Now what I'm going to do is I'm going to pick 5 samples here randomly. So these here, as you can see, 5 samples I am picking randomly. This n is equal to 5. And then once I have picked up these 5 samples, I calculated their mean, and that is my distribution of means. And as you can see here, since the points are more or less here, the mean has to be here, right? This is only one point here, so this mean is like very close to these data points. So again, I choose randomly 5 points. I get a mean, which means like I'm here. I've got these 2 points, and I have started forming my distribution of means. I've got 2 points. Here I've got 2 points. Again, one more. I've got 3 points now for my distribution of means. And as you can see, I've done like 3 repetitions. Now what I'll do is I'll like fast forward. I'll do it 10,000 times. Now it's like 10,003 times because I did 3 times before, and now it's 10,000 times. Now for this distribution of means, if I want to feed it to a normal distribution, I can see that it's more or less fitting like a normal distribution. So my hypothesis 1 is proved, and we can see that it works here. What was the second hypothesis? That this distribution of mean and this mean will be coming very close to each other. And if I look at it, it's like 15.47 here, and here it's 15.5, very, very close. If I do it, say 10,000 more times, now I have done 50,000 times, and as you can see, this mean is like 15.49, and this mean is like 15.47, very, very close. If I take 1 place of decimal, then it has already merged. My third point was standard deviation. So standard deviation for the formula was sigma x bar is equal to sigma by square root of n. So in this case, sigma is my 9.96, which is this, divided by square root of n. N is, I'm taking 5 samples, so square root of 5. So now let's just calculate and see how much it should come and how much it has come. So square root of 5, I guess, should be 2.23. 9.96 divided by 2.23. That is 4.46. And you can see here it's 4.45. Very, very close. So let's do one more. And it doesn't matter how many number you choose. It will still stay the same. Another distribution. Animated. I'm now taking 10 samples and then I get my distribution of means. So here my standard deviation is 9.14. So first let's do 10 square root. 10 square root is 3.16. So 9.14 divided by 3.16 is 2.89. So here my sigma x bar should be 2.89 after few iterations. We'll see. So animated again, 10 samples, and I get their mean. Now fast forward, 10,000. I have tried to fit the normal distribution, and I can see it's almost fitted, or it's fitted quite well actually. Here the mean is 14.38, the mean is 14.41, almost merged. The standard deviation is 2.93, and we should have got 2.89. Again, very close. Let's do few more rounds and see. Now after 60,002 rounds, we can see now the standard deviation is 2.9. Here this is 2.89. Here we see that the mean is 14.39. Here you can see the mean is 14.38. And now it fits the normal distribution even better. So you can play around this tool and get a very good idea about central limit theorem. And in the next lecture, what we'll do is we'll look at hypothesis testing. We'll understand what is a null hypothesis, what is an alternate hypothesis. Then we'll look at false positive, false negative, type 1 error, type 2 error. And then we'll look at some problems. So in order to do hypothesis testing, which we will learn later in the next series, the basic building block is central limit theorem. So we apply central limit theorem and get answers of hypothesis testing. So here, this part, this analysis, under a lot of scenarios, we use central limit theorem. Not that for this case we will use central limit theorem, but just assume that if we go this path, central limit theorem, and there are other techniques as well, not only central limit theorem, but in this context, so we establish a hypothesis, we collect the data, we do some analysis by using central limit theorem and or some other techniques, and then we calculate the p-value, and then we make some inferences. And central limit theorem, as I said, is one of the most powerful techniques in statistics. So I hope all of you liked this session. If you want to subscribe for the course, you can click on the below link. And if you have liked this session, I request all of you to share, click the bell icon, subscribe to this channel so that we can make more content and we can try to make statistics much easier to understand for all of you. Having said that, I thank all of you for watching this video and happy learning.
To know more, follow and subscribe to upGrad.